find the radius of convergence, we simply apply the ratio test. So here we have the limit as n goes to infinity of the absolute value. You know that in the absolute value, this negative 1 to the n will go out. So all we have here is x to the n plus 1 over n plus 2 divided by x to the n all over n plus 1. The ratio test is the limit of the absolute value of the a sub n plus 1 sequence term divided by the a sub n term. So the limit is n goes to infinity of the absolute value. This is x to the n times x, that n plus 1 comes upstairs. This is divided by x to the n times n plus 2. Now the x to the n's cancel. This leaves us with the limit as n goes to infinity of the absolute value of x times n plus 1 divided by n plus 2. You recall that for the ratio test for convergence, we got to have this limit being less than 1. The limit, the factor of the limit is being determined by n, not the x. We know that the n values are positive. We don't know the whereabouts of x. X could be positive or negative. So we definitely leave x as the absolute value. So if you think about it, that we have here the absolute value of x times the limit as n goes to infinity of n plus 1 all over n plus 2. Now the limit of n plus 1 divided by n plus 2, this guy is equal to 1. But for convergence, for the ratio test, you want this whole term to be less than 1, right? So this implies then that we have, look, now this limit here, this limit is equal to 1. So we have what's left, the absolute value of x times 1 is less than 1. Right, the absolute value of x, this limit is 1. We want, for the ratio test, for convergence, we want this limit of the absolute value of the a sub n plus 1 divided by a sub n to be less than 1, right? So if that's the case, then we check the endpoints. Notice that this, by definition, is negative 1 less than x less than 1. So we now here they only wanted us to find the radius of convergence, and so the radius would be this r is equal to 1. I'm going to go a step further and just find the endpoints. We need to do that for the next problems, but it's always good to get a catch and feel for it even now. So check x equal to negative 1. You're going to take x equal to negative 1 and plug it back into the original series. So this is the summation as n goes from 0 to infinity. You got that negative 1 to the n. That's necessary. Then x is negative 1. This is to the nth power, and that's divided by n plus 1. Now negative 1 to the n times negative 1 to the n will just give you positive 1. Right? So this is negative 1 to the 2n. And so negative 1 to the second power is positive 1 raised to the nth power. 1 to the nth is just 1. So this is 1 over n plus 1. Does this converge or diverge? This is P series divergent or harmonic, right? So the whole series is not divergent. It's divergent at x equal to -1. We're checking the endpoints. Now let's check at x equal to 1. So we have the summation is n goes from 0 to infinity of -1 to the n times 1 to the n all over n plus 1. This is the summation as n goes from 0 to infinity of -1 to the n all over n plus 1. Now positive 1 to the n is just 1. So this is alternating series convergent. So the interval of convergence is open at -1, comma, closed at 1. Here with radius is at 1. So with the radius, r is equal to 1. Let's do the same thing here for number 11. I have 3 problems, probably 4, but 3 I want to show you where the interval of convergence is at a point, the interval of convergence is an interval, and the interval of convergence is the entire number line. So we apply the ratio test. So this is the limit as n goes to infinity of the absolute value of x over 4 to the n plus 1 divided by x over 4 to the nth power. So this is the limit as n goes to infinity of the absolute value of x over 4 to the n times x over 4 divided by x over 4 to the nth power. So the x over 4 to the nth power cancels out. So we have left the limit as n goes to infinity this is the absolute value of x over 4. For the ratio test to be convergent, we want the limit to be less than 1. Now the limit of x over 4, notice here that this is as n goes to infinity. So this x over 4 is a constant in comparison to n, because n is the one that's changing. X is a fixed number that was supplied by the user. We don't know what that number is. So this is the limit of a constant, which is a constant. So here we don't know if x is positive or negative, so we leave it in the absolute value less than 1. This implies that the absolute value of x is less than 4. So 4, the radius is equal to 4. We check the endpoints. So we check at x equal to -4. Because here, by definition, this is defined as -4 less than x less than positive 4. So we check at x equal to -4, plug that back into the original problem. So we have the summation as n goes from 0 to infinity. Here, this is x is -4 divided by 4 to the nth power. This is the summation as n goes from 0 to infinity of -1 to the nth. A negative 1 to the nth power is equal to, when n is 0, we get 1. When n is 1, we get negative 1 plus 1, negative 1 plus 1 plus, well, it'd be negative for the next one. 1 minus 1 plus, and so on, plus 1 minus 1 plus, and so on. So what's that? What's this limit? Well, here's the thing. This series is oscillating. 1, so it's not monotonic. It's going to plus 1 minus 1. And it's not strictly increasing, neither is it strictly decreasing. So it fails the Hanna-Borel theorem that says that for a series that is monotonic, and also that it also um, is bounded, if you will, that means it's not oscillating, that particular series is said to be convergent. This series is not. Convergence means that we're traveling to a number, and we're gonna deaden out. But here, this keeps on traveling to plus or minus 1. Here, since the series the series oscillates. I was having trouble trying to remember how to spell oscillate, and I probably still got it wrong. Between negative 1 and plus 1. And here the so-called sequence values. And the sequence values are not monotonic. Monotonic means that whatever it's doing is going to do that same thing. So either it's going to be increasing, going up always, or it's increasingly going down, right? So it's non-decreasing or non-increasing. So it diverges there. But let's check at x equal to 4. So this implies here that we have summation as n goes from 0 to infinity of 4 divided by 4 raised to the nth. This is the summation as n goes from 0 to infinity of 1 to the nth power. This is 1 plus 1 plus 1 plus and so on plus 1 plus and so on. That's equal to infinity. So it diverges. So the endpoints, we have divergence, but within the interval, we have convergence. So the interval of convergence is the open interval from negative 4 to 4. Okay. The next problem. So here this gives us an interval of convergence, right? Pretty neat. So here we apply the ratio test. So the limit of x to the 5 times n plus 1 all over n plus 1 factorial. That's divided by x to the 5n divided by n factorial. We'll simplify this. This is the limit as n goes to infinity of the absolute value of, this is x to the 5n plus 5, or times x to the 5th, and that n factorial comes upstairs. This is divided by, now n plus 1 factorial is n plus 1 times n factorial. I'll just write it here. And this is times x to the 5n. Now x to the 5n's cancel. So this is the limit as n goes to infinity of the absolute value of x to the 5th times n factorial, and the n plus 1 factorial is n plus 1 by definition times n factorial. So the n factorial cancel, right? Now I see what's happening. I'm looking at the future, and everything you do, you want to always look the next step. That's in mathematics, that's what we're taught. So looking at this, if I pull out the x to the 5th, the limit of 1 over n plus 1 is going to be 0. So I know that this guy can be bounded above by 1. To satisfy absolute convergence for the ratio test, right? It has to be less than 1. So notice here that I have the absolute value of x to the 5th times the limit as n goes to infinity of 1 over n plus 1. Now, this is all less than 1, right? But this limit here, this limit is equal to 0. You can see that. As n goes to infinity, 1 over n plus 1 goes to 0. Interesting. So what this implies is that implication that I have the absolute value of x to the 5th times 0 less than 1. That is, 0 is less than 1. Well, obviously. Well, what this means that for any choice of x, it doesn't matter for x, I will get convergence all the time. I will always get whatever value of x you put here times 0 is going to always be less than 1. X could be a million. A million to the 5th power times 0 is still 0 less than 1. So here this series converges for any choice of x. That is, the radius can be anything. The radius is infinity with the interval of convergence as the interval from negative infinity to positive infinity. Now, when you get that limit equal to 0, then you have convergence everywhere, right? Now, in number 11, we actually got some interval, right? Pretty neat interval there. Here, for number 15, the interval we do have, but it's everything, right? So look at this one. So here we apply the ratio test, the limit of the absolute value of 2 in parentheses n plus 1 factorial times x over 3 to the n plus 1 is all over 2n factorial times x over 3 to the nth power. So this is the limit. Simplify everything as n goes to infinity of the absolute value. Now you see here that x over 3 to the nth will cancel with this x over 3 to the nth. You have left x over 3 up in the numerator. Well, I still write everything out. This is 2n plus 2 factorial. That's the next term because these are even values. This is x over 3 to the nth times x over 3. That's all over 2n factorial times x over 3 to the nth. Now, this is simplified. This guy goes out. Right? Need to simplify this 2n plus 2 factorial because that's 2n plus 2 factorial times this. That's 2n plus 2 times 2n factorial. I get it right. So this is 2n plus 2 times the 2n factorial. The 2n plus 2, if you had 6 factorial, you can write that as 6 times 5 factorial, right? And you can write that as 6 times 5 times 4 factorial. You can write that as 6 times 5 times 4 times 3 factorial. You can write that as 6 times 5 times 4 times 3 times 2 factorial, which is just 2 times 1. You get the point, right? So, I mean, but you can just stop and say 6 factorial is 6 times 5 factorial. So if you had, say, for example, 6 factorial divided by 5 factorial, this is 6 times 5 factorial all over 5 factorial. You have left with 6. That's ideally what we're doing. Right? And so this is times x over 3 is divided by 2n factorial. The 2n the 2n plus 2 is there, but the 2n factorial cancels out. Too many colors, like the Joker. Anyway, so this is the limit. I like the Joker. He's pretty cool in Batman. This is the absolute value. Let's see what we have here. This is 2n plus 2 times x, and this is all over the 3 downstairs. Well, it's a pretty lazy 3. Now, let's see if we can see this. This is the limit as n goes into infinity. Let me back up. The n is going to infinity, right? But the x and the 3, well, they're just sitting there. They're fixed constant terms. So I'm going to write this as the absolute value of x over 3 times the limit as n goes to infinity. And this is just 2n plus 2. Now, I better not say this is less than 1, because notice that here as n goes to infinity, 2n plus 2 also goes to infinity. So I have the absolute value of x over 3 times infinity. That's infinity. So I get divergence, right? So here the series diverges. But does it diverge everywhere? It does, except at one value. That is when x is equal to 0. We get something good. Well, notice if x is 0, I have the summation of 0, which is just 0. That's convergence. So anytime you get the limit here to equal to infinity, go back and check for convergence at one point. notice that the series diverges everywhere except at its center. Here, I'm looking at this guy right here. That's the strength of it, right? If this x over 3 equal to 0, this implies that x is equal to 0. If this was in parentheses x minus 2 to the n, then the center, obviously, x equal to 2 is the center, right? This is not a problem, but this, you get the idea. Here I don't have x minus something, so I can't say that c is equal to 2. I don't have that. Here the center is 0. That's the idea. So here at its center, and that is at x equal to 0. So what's the radius? The radius is 0. So here I have the number line, and I have here this number c, right, which is 0, the center. And we say that the radius, now I need the big guy. Oh, there it is, even bigger. The radius is that. The radius equals 0 says you don't move from this point, x equal to 0. You know, x equals 0, c equal to 0. Right, same thing, right? Because beyond moving from this radius, I get divergence. But at c equal to 0, right, here, that is x, the number x equal to 0. When x equal to 0, I get convergence. These values are they're really relative. C is a number of x, right? So notice that the series diverges everywhere except at its center, x equal to 0. Thus, r is equal to 0. That's the radius. Right? You move no units from the center, and you have convergence. Now, I'm going to do one more, and then I got to go eat my Chinese stuff, right? Chinese food is good from Foolin's in Madison. Leftovers from last night. Asked the guy to give me extra rice because I knew I would come here today for lunch. Okay. So now apply the ratio test on this guy. Looks very big, but no problem. I'm getting a message on my phone. Somebody's trying to tell me something. Now the absolute value in that -1 to the n plus 1 is going to be insignificant with the absolute value. So I'm just going to take everything else that I have. This is x minus 4 to the n plus 1. This is over n plus 1 times r, well, 9 to the n plus 1. And this is now all over x minus 4 to the nth divided by n times r to the n. So this is equal to the limit. We're going to simplify all of that as n goes to infinity of the absolute value of, this is x minus 4 to the nth times x minus 4. And then downstairs, this guy comes upstairs. So this is times n times 9 to the n. This is all over, yes, n plus 1 times 9 to the n times 9 times x minus 4 to the nth power. Let's see what cancels. This x minus 4 to the nth, this 9 to the n, right? Okay. Make the music with your mouth, biz. Okay, so now we get the limit as n goes to infinity. So what I have is an n, an x minus 4, So x minus 4 times n. This is all over 9 times n plus 1. All right. Now, do we get convergence here? You better believe it. Look at the n terms, right? N divided by n plus 1. The limit of that is 1. So we can force this to be less than 1 because you got other stuff operating. You got this x minus 4. You got this divided by 9, right? So for convergence, for the ratio test, say less than 1 because I look, if this was just n up top and there was no n plus 1 down there, this limit would go to infinity. I couldn't say less than 1. All right. So this is to say, look, I'm going to write this. We can pull out the x minus 4 over 9. Just put that in absolute value. Because here the limit is with respect to as n is changing, not x. Right? This is times the limit as n goes to infinity of n over n plus 1. And we're saying here this we restrict this to be less than 1. You can do that because you have power. This limit here is 1. So I have the absolute value of x minus 4 divided by 9 times 1 less than 1. So that is, we have the absolute value of x minus 4 over 9 is less than 1. Right? Now, you can multiply both sides by that 9. So that is, the absolute value of x minus 4 is less than 9. And by definition, if and only if, negative 9 is less than x minus 4 is less than 9. So we add 4 throughout, so that gives us negative 5 less than x less than 13. We check the endpoints. You see, I had said earlier in the previous video that when you have x minus c is less than r, you got to be careful how you write that and how you extract from that then the so-called interval of convergence. You see here I have this form, but the actual interval of convergence is, for this problem, negative 5 less than x less than 13, because you have to deal with that c term here associated with x. So okay, you didn't get that. Okay, it's okay. It's okay. Just check the endpoints. You know, some things in life you just might not get, but it's okay. Hopefully it will come together after a while. Check here, x equal to negative 5. Oh man, it's a long, big problem up there. See if I can capture it and bring it downstairs. Good. So we have here, that's the summation as n goes from 1 to infinity. This is negative 1 to the n plus 1. X is negative 5 minus 4, right? So that gives us negative 9 to the nth all over n times 9 to the nth. Simplify. We want to cancel this out, but it's a negative there. So we're going to pull out negative 1 to the nth power. So this is the summation as n goes from 1 to infinity. Negative 1 to, I'm going to write this as negative 1 to the n times negative 1. And then times negative 1 to the n times 9 to the n. Do you understand that negative 9 to the n is the same thing as negative 1 times 9 raised to the nth, and this is negative 1 to the nth negative 1 to the nth times 9 to the n. Okay. Divided by n times r to the nth. So r to the n cancels out. Negative 1 to the n times negative 1 to the n becomes positive 1, right? So this is the summation, as n goes from 1 to infinity, of, this is negative 1 all over n, right? So isn't this p-series divergent? It's harmonic. You can look at this as being negative times the summation. Has to start at 1. This is p-series divergent. We call it harmonic. So now we check at x equal to, checking these guys, check at x equal to 13. So plug that into the original summation. Doesn't look good. It's negative 1 to the n plus 1 times x is 13. 13 minus 4 is 9 to the nth all over n times 9 to the nth. We apply the law of cancellation. Summation as 1 goes to infinity. Here this is negative 1 to the n plus 1 all over n. This is alternating series convergent. So the series was divergent at negative 5. All right, we got harmonic, but it was convergent at 13. So it was open at negative 5, comma, closed at 13. I think that's pretty good, a pretty good overview of this section. Thank you. Oh man, 39 minutes. Didn't mean to hold you that long.